All right. Well, as we get started, the seniors have just been on their senior trip. We've spent the first half of the class time talking about senior trip, and we already went over the quiz they took in the last lesson. I want to quickly review some things for the sake of the video that we've already gone over by going over the quiz. We talked about two types of circuits. Remember we said for a circuit, you've got a battery, and then the current will flow through some resistances and may come back to the battery. This would be an example of what type of DC circuit, class? A series circuit, because the current goes through one resistance, then the next, then the next. We said for a series circuit, equivalent resistance is simply the sum of the different resistances. You just add them up. We also said that to find the current that's able to flow through this particular circuit, you're going to divide the voltage that the battery is able to provide. Remember, the voltage is like that push that forces the current to flow. Remember, we said that the resistance would naturally keep free electrons from just whizzing through. You hold a piece of copper wire, there's delocalized electrons. They're really not going anywhere yet. You need to give them a push to start them flowing in one direction. That's what the battery does. It gives that push, and the voltage divided by the equivalent resistance tells you how much current can flow through the circuit. We said that the current that leaves the battery is the same everywhere because there's only one path. The current can't split. The mass of students at Grace Christian School can't necessarily all take different stairwells because there's only one route. Okay, that's illegal by fire code. Okay, that's not the case here. But imagine if it were. Everyone has to go out one door. That's going to get very congested. That explains why resistance would be higher here. But whatever current can leave the battery, whatever current can flow, all of it goes here, all of it goes here, all of it goes here. As the current goes here, it uses up voltage to push that current through. So there's a certain amount of IR drop or voltage drop at that resistance. Well, then more voltage gets used. There's another IR drop at this resistance. Then there's another voltage drop at the next resistance. As that voltage gets used, the last remaining voltage is used at the last resistance. So we see that the electrical potential difference or voltage just gets less and less and less as it goes around. So the voltage varies by resistance, but the current is constant in the series circuit. We also looked at DC circuits that looked something like this, where you had a pathway, but then we added another pathway, then maybe added another pathway, and we could keep adding if we wanted to. We could add more and more pathways. This would be an example of a parallel circuit, right, where you've got the current choosing where it wants to go. There's different pathways for it. Well, whichever of these resistances has the least resistance, that's where most of the current will go. Less and less depending on the amount of resistance. So the current, whatever current does leave the battery, which will still be found the same way, will choose the path of least resistance. Current will vary based on the resistance in each branch, if you will, of this parallel arrangement. But we said the equivalent resistance is always less than any individual resistance because let's just say this is the least resistance. Well, by adding a whole other pathway, all we've done is diminish total resistance. So here, remember, we used reciprocals and use that reciprocal button. The reciprocal of equivalent resistance is the reciprocals added together and so forth. And so we said that the voltage that the battery provides in a true parallel circuit, all the voltage goes at once. So there's one consistent voltage, one consistent amount of push, all of the resistors the same way. So that voltage was constant, current would vary in the parallel circuit. What we're going to get into today, and this is our last concept for the year, okay, so we're going to finish this out. We're going to take several days to work our way through this. What if you've got series and parallel at the same time? Well, then we have something called a network. Next item in your notes, a network. I remember my senior year, Audrey, I'd been told that I was the class valedictorian. And it was a really intense competition. There were about a dozen other kids kind of fighting for this spot. And I managed to win out. And once I heard that, it was like, yes, success. And mentally, I checked out, okay? And so I remember my teacher getting mad at me for not understanding this. Shout out to Miss Dawn McKenzie. And a great teacher, but she got upset with me. She's like, I'm going to tell her to revoke your valedictorianness. You're not going to pay attention. I tried. It was just hard, okay? I struggled to understand this in high school. I also struggled to understand it in college. But I've had really good success helping high schoolers understand it. So stay with me. We're going to spend a few days. You're going to understand this so that if you take it at the college level, and Michael, you probably will, you'll already have a leg up on those folks because you should understand it really well. All right, so networks. A network is a complex circuit with loads or resistances in both series and parallel arrangements. It's a complex circuit with loads in both series and parallel arrangements. By the way, for those watching on YouTube, if you're wondering, the seniors pranked my room before senior trip, and I've managed to leave up a little bit of it. They had You've Been Foiled, and they wrapped everything in the room in aluminum foil, and they said, ha, we found X without math, and there's X on the wall, as you can see. So anyway, my lectern is still somewhat wrapped in aluminum foil and a graduation banner that they congratulated themselves with. So anyway, for sake of your viewing, I'm going to zoom in just a little bit more here, but I did want to explain the foiled stuff there. They did a really good job of pranking the room, I will say that. All right, on the record. All right, so a network is a complex circuit with loads in both series and parallel arrangements. How to solve a network. Now, we're not going to do all of this today. We're only going to do the first 3 steps. There are 5 steps. We're going to do the first 3 and work on mastering those steps today. First of all, you're going to replace, either physically or mentally, on the schematic, any simple series with its equivalent resistance. Replace any simple series with its equivalent resistance. Why? Because this is stupid easy. You find resistances that are in line with each other, you add them together, and now it's one resistance instead of multiple resistances. Makes it easier. Once you've done that, you may have some simple parallel resistances. So, replace any simple parallel with equivalent resistance. And again, I know it requires the use of reciprocals, but it's really not hard to do. It may require memory values because reciprocals sometimes work out with crazy decimals, but it's still not a hard process. Once you've done that, you may have recreated more simple series. And when you simplify those, you may recreate more simple parallel. So step number 3 is kind of a vague, repeat steps 1 and 2. Until the equivalent resistance of the network is found. Repeat steps 1 and 2 until the equivalent resistance of the network is found. You just keep at series, parallel, series, parallel, series, parallel, until eventually this is the equivalent resistance. This is as far as we're going today. Tomorrow, once we've mastered this process of figuring equivalent resistance, then we're going to spend the next couple of days working on steps 4 and 5. Step 4 really isn't hard. It's step 5 that's the kicker. Step 4, determine the total current in the circuit. Determine the total current in the circuit. Again, that's easy. Once you know the equivalent resistance, voltage divided by equivalent resistance is total current. We've already been doing that. So that's really not a hard step. We won't do that today only because the reason we need that total current is to do the last step, which is something we're not getting into yet. Now, it's something we've done, but we've done it for series. Or we've done it for parallel. Remember that little chart we make where we find the current through every resistance and the IR drop at each resistance? That's the end goal. That's the harder part that we're going to hold off on. So find the current through each load and the IR drop at each load. Find the current through each load and the IR drop at each load. Again, those last couple steps, we're going to save that for tomorrow. But go and get it in your notes now so they're all together. Let's look at an example first, and then we'll do some problems together here, finding equivalent resistance. Look in your textbooks, if you would, at page 390 with me. Page 390. Looks like we've all got that copied down now. Page 390 at the top of the page, they've got figure 25.12. I want to kind of talk through it with you here. We see that there are 5 different resistances or loads. They're marked as resistances, but again, they're probably just lazy, so like me, they just put the squiggle instead of the squiggle with a circle around it. Looking at the top of the page, we don't need to mark anything else on the page right now. We've got one simple series. Do you see it? It's in that second branch of the parallel. Do you see how there's 2 parallels running next to each other? There's a 12 ohm resistance in one branch In the next branch, there's two resistances, a 5 and a 10, but they are series with each other. Does that make sense? They're within a parallel, but they are series because they're one after the next. So all they did from figure A to B, the only change is instead of a 5 and a 10, they just put a 15. See, pretty easy? You could probably do that mentally, honestly. You probably don't need to redraw the schematic to see that, but you could, and they did. The next thing you see is that the 12 and 15 now are in simple parallel with each other. Does that make sense? There's nothing else going on with those two. They're just a straight parallel. So they used the reciprocal 12 plus reciprocal 15 and took the reciprocal of that to get 6.6 repeating, and they replaced the parallel with just that one resistance. Does that make sense? Then finally at the end, they said, well, now look what we've got. We've got 3 resistances, and they're all in series with each other. So we just add them up. 8 plus 6.6 repeating plus 20 gives 34.6 repeating ohms, and that's your equivalent resistance. You see what they did? All right, on your paper, let's go ahead and do a couple of these together. Let's start with one that's even a little easier than what the book has. Draw your battery, and then from the battery, have the current pass through a 3 ohm resistance. From the 3 ohm resistance, let's have the current go into a 6 ohm resistance. From there, have the current go through another 3 ohm resistance and back to the battery. Now that, what I've drawn is basically just a series circuit. What I'm going to do is I'm going to add one extra path right here with an extra 6 ohm resistance in it. Now I've made it a network because now it has series, but it also has parallel. Does that make sense? Now the way I will typically solve one of these, I will typically not redraw everything because, lazy. So what I will typically do is I will circle groupings. I can see that these are simple series. And rather than redraw, off to the side, I'll just say, I know that this resistance right here is really how much, class? Mm-hmm. This is really 9 ohms of equivalent resistance right there. I also see that this is simple parallel. So I'll replace that, well, I'll get the calculator out actually, and we'll use reciprocals, remember? Don't forget the reciprocal at the end, by the way. And how much equivalent resistance is right here in the parallel class? 2 ohms. Right? We all have 9 ohms for the 2 simple series and 2 ohms for the simple parallel. Now, if I were to redraw this, and you don't necessarily have to, but does everyone see that I would have a single 9 and a single 2 if I were to redraw it? So what's true about the 9 and the 2 now? They are in series again, aren't they? So I would just add those together to get an equivalent resistance class of 11 ohms. I don't necessarily need to redraw this because I can see that those 2 circled groups are in series with each other. There's my 11 ohms of equivalent resistance. Usually that's what I'll do unless it's a really complicated network. This one's pretty easy. I'll take shortcuts because lazy. All right, questions on this? Let's draw another. Let's make this one more like what we had in the book then. We'll use different numbers, of course, than what they used in the example we looked at a moment ago. But let's have the current come out from the battery. And let's have it go through a 4 ohm resistance. Let's then have it go through a 5 ohm resistance. Then through a 2 ohm, that's a terrible omega, 2 ohm resistance and back to the battery. Again, right now it looks like a simple series. Let's add, however, an extra branch with 2 ohms and 3 ohms in it. Again, now we have a network. Now, some students will say, hey, the 4 and the 2, they're simple series. Well, I can see why you'd say that, but they're not connected directly to each other. There's this parallel stuff that as the current flows from here, the current has to split up and go through all of that before it ever gets to the 2. I would argue the 4 and 2 are not simple series. Okay, you could confuse yourself that way because there's stuff in between them. If the 2 were right here, then 4 and 2 would be simple series. Or if the 4 were down here, okay, then 4 and 2 are simple series. Does that make sense? But what we do have as a simple series class would be the 2 and the 3, just right here. So I'm going to circle it, and I'll replace 2 and 3 collectively with 5 ohms. By the way, I want to point something out to you. Don't redraw this, but I do want to show this, because this is something that tends to throw students off. Do you see that the 2 and 3 are still in simple series? Because once the current goes, here's your junction point, right? The current comes from the battery, goes through the 4 ohm resistance because there's nowhere else to go. Once it hits this point, the current either goes through this branch or through that branch. Does that make sense? So even though they're not drawn next to each other, and on most schematics they would draw them that way, but even if they're not, do we see that the 2 and 3 still are simple series with each other? All right, then the current from this branch and this branch reconnect, and then everybody has to go through the 2 ohm branch. Does that make sense? All right, so these are simple series, even if they haven't been drawn the way you've got it on your paper. Now I've got one simple parallel. The 5 and the 5 are simple parallel with each other. So use reciprocals. And what is the current going to be for the simple parallel? 2.4. Comes out to 2.5 ohms. Now at this point, you may feel like it would be good to redraw the circuit. You certainly could. However, you realize that means that all of this up here, all this stuff, is basically 2.5 ohms. So we have the current going through 4 ohms, 2.5 ohms up here, and then 2 more ohms. Do you see they're all simple series now? So now we just add them together to get, careful, 8.5. 4 plus 2 plus 2, 8. So 8.5 ohms of equivalent resistance. Does that make sense? Simple series, make it just an individual single resistance, or equivalent resistance, if you will. Simple parallel, then back to simple series. If we had more simple parallel, we go back to that. Then if we had more simple series, back to that, and so on and so forth. Questions? Turn over, or look across the page, rather. You were on page 390. Let's look at page 391. Now this one's a beast. Okay, so this is one where we're going to do a little bit of redrawing here. I don't want you to draw it on your paper. I just kind of want you to follow along at the board, because the ones you'll work on quizzes and tests will not be this complicated. But I want to kind of show the whole equivalent resistance process where you may have to go back and forth multiple times. The other advantage I have is an eraser. If you were to do something like this for homework, for instance, pencil, lightly drawn and easily erasable, may be your ticket, as you'll see here in a moment. They've got the battery drawn at the top of the network, and then the current goes down and splits 3 different ways. It goes to a single resistance, or a couple of resistances, or a single resistance. You see the parallel here. The current then all reconnects from these 3 pathways. Every bit of the current has to go through this resistance down here at the bottom, the one labeled R8. Do you see it? Then from there, the current gets to split again. And it's got a pathway that takes us pretty close to the battery, or it's got a pathway that goes through a resistance, splits again, and then they've got another pathway that has 2 straightforward resistances. All of this reconnects. And then there's one last little resistance before they hit the battery. All right, do we see what we've got going on here? All right, so that's what we see at the bottom of page 391. It says assume everybody's 4. So I'm not going to go through and label them all as 4 because they're all 4. What I'm looking for first are any simple series. And there are 2 simple series. You may look at your books, you can refer to them as resistance and then by the number. Which resistance numbers are in simple series, class?
1 and 2.
Okay, 1 and 2 over here. By the way, 1 and 2 doesn't mean they're the first and second resistances. They just labeled from left to right. But resistances 1 and 2 are simple series. So I'm going to erase the pair of 4s and replace them with a single 8. Everybody else is 4, but that one's 8. That make sense? There's another simple series. 10 and 11, which are these ones here. They're simple series. So again, 4 and 4 gives me 8. That's a single 8 resistance. Now we look for any simple parallel, and there are two places where there's simple parallel. Where do we have simple parallel?
3 and 4.
Do you see that the 3 and 4 right here are simple parallel with each other? Now, not these ones with them, but just those two make a simple parallel. 4 and 4 use reciprocals, gives what? That becomes essentially just a 2 ohm resistance. Now there's two separate things, right? There's actually physically two separate loads there, but as far as the resistance that is created, they might as well just be 2 ohms of resistance. Make sense? Where's the other simple parallel? Over here now. It wasn't simple parallel, but now the 484 is simple parallel. Does that make sense? By virtue of taking the two 4s and making them an 8. So now 484 use reciprocals. What is the equivalent resistance over here?
1.6.
I got a 1.6 evenly?
Mm-hmm.
Okay, nice. All right, so all of that basically becomes, you see the use of the eraser, this basically becomes a 1.6. All right, do we have any, that was parallel, right? Now back to simple series. Any simple series is?
Mm-hmm.
Where?
For the R3, R4, and then R5.
Right here, right? We had a 2 and a 4. Well, they used to be a pair of 4s. We got basically 2 and 4. Collectively, class, that makes 6. So that all just becomes 6 ohms resistance. Don't forget, this is a 4, this is a 4, this is a 4. Now there aren't as many, I'll label them. All right, any other simple series?
The 1.6 and 4.
The 1.6 and 4 right here might as well be, class,
5.6.
5.6. So I can replace all of this with a single 5.6. Okay, that's simple series. Now we go back to simple parallel. And I do have a simple parallel. The 864 is simple parallel. Using reciprocals.
1.84615.
I got a 1.846 blah, blah, blah. Save that in the memory of your calculator. All of this might as well become
1.85.
1.8 blah, blah, blah. Memory 1. Now, that was parallel. Now back to simple series. Do I have any simple series?
Mm-hmm.
That's all it is now. So I've got the memory, plus I got 5.6, plus I got 4, comes out to
11.445.
11.4 blah, 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 blah. And you actually have to turn the page because it took so long to solve it. But we see the 11.44 blah, blah, blah. The next page, there's our equivalent resistance. Now again, you won't have to solve networks this crazily, but do you see how it goes back and forth? Take care of your series. Don't worry about anything else. Just if you see simple series, take care of those. All right, now, do you see any simple parallel? Take care of that. Now, any simple series? Take care of that. Do you see the back and forth? Series, parallel, series, parallel. Just take care of the little things as we go. Page 399. Page 399. And let's take a look at problem number 10. This is not as bad as what we just looked at, but I want you to get out on a sheet of paper and a pencil and lightly sketch number 10. Do this one with me. You watched on the last one. This one I want you to do along with me. So right off the bat, you see that the current has a chance to split. The current doesn't go through anybody before it splits. It splits and goes through R1, and then it has a choice of options. It could go through R2, actually it could go through either R1, R2, R6, but if it goes through the branch that has R2 in it, the current that goes through R2 will have to pass through a split. And I'm going to run out of room here. All right, so we see this diagram. Hopefully you draw it better than I did. Ran myself out of room. I think I'll just lengthen these actually. Keep nice straight right angles. And it tells me that all the resistances here are how much, class? 8 ohms. Everybody's 8. All right. Any simple series?
Mm-hmm.
Where?
Bottom right of the parallel.
4 and 5, right? Bottom right of the parallel. 4 and 5. Everyone sees that. So let's replace the 8 and 8 class with
16.
All right. Any other simple series? No. All right, simple parallel. Be careful. Just the 16 and R3. Don't call these simple parallel. They're not. But R3 and 16 are. So this, remember, R3 is 8. So 8 and 16 gives us what? Someone else got the same thing? So this basically becomes 5.3 repeating. We don't need to use a memory because we can just type a bunch of 3s if we want them. Or we can even type 5 and 1/3. All right, now do we have any simple series? What do we got?
8 and 5.3.
The 8 at R2 and the 5.3 repeating. So collectively, this branch becomes what?
13.3 repeating.
Now be very, very careful here. Any simple series, actually that was simple series, any simple parallel, sneaky. They want you to fall for this. Oh, these 3 are parallel, but they're not. Why not? This little guy down here. Only these 2 are simple parallel because the R1 is separated from the other guys by virtue of current that flows through R1 comes back here. Current that flows through these 2 has to go across R7 before rejoining. Does that make sense? So just the 13.3 repeating and this 8 ohm resistance at resistance 6, they're simple parallel. Stay with me. What do we get for the equivalent resistance here?
5.
Evenly? 5?
4.99.
So pretty much 5 then. Okay. So if you actually typed in 13 and 1/3, you would get 5. So all of this just becomes 5. I'm going to go ahead and write 8s for these 2 guys. Now, do we have any, that was parallel, any simple series?
5 and
Do you see that this 5 and this 8 are simple series with each other? So collectively, they become 13 ohms evenly. Does that make sense? Now back to parallel. And of course, it's just the one thing here. The 8 and 13 collectively give us
4.95.
evenly? Or continues on? 4 point
5, 2, 3.
blah, blah, blah. All right, I assume they gave us 2 sig figs. They said 8.0 ohms. So we'll round to 2 sig figs and it comes out to
5.0.
5.0 ohms of equivalent resistance. Despite having, by the way, 7 different 8 ohm resistances. Had they all been in a line, that's 56 ohms. But because they weren't all in a line, it's 5 ohms. Questions on this? All right, no written homework tonight. Give you a chance to let your brains catch back up with all of this. But do we feel like we've got a good grasp of the equivalent resistance in the back and forth? Okay, because tomorrow we're going to review it, and then we're going to actually get into finding those currents and IR drops and stuff like that. All right, have a wonderful rest of your day, and you are dismissed.